have a number of points to go through here. Bootstrap. Here are the bootstraps. That's the von Münchhausen thing now. Now we're going to use this simulation thing to redo the kind of statistics that I already taught you in a way before the break. And Peter, who was here. 1 and 2 sample mean comparisons in confidence intervals. That's what I taught you before the break. Now I will let the computer help me do it. The big thing in doing the statistics was to be able to use the right sampling distribution for whatever we compute. When I compute a mean, I needed to find out that the sampling distribution of a mean is a t-distribution, that it can be different from time to time like a t-distribution, and I use this t-distribution to do my statistical conclusions, the confidence interval or the hypothesis test. Now we'll let the computer find the sampling distribution for us. We will not base it on some theoretical, some probability guys made that tool for us, right? I say my data is normal, now I want to do statistics on the mean. How could I do that? Well, the probability guys use some of those rules that I mentioned and find out the right sampling distribution is the t. It's pretty complicated to prove that. If you've seen some of the extra math movies, you'll see it requires a little bit. Not rocket science, but still a course or two. It comes in 2 versions. It's pretty fantastic what you get in these 45 minutes now. Very, very general, but also specific on the 1 and 2 sample. That's where I'm going to teach you for the 1 and 2 sample. It comes in the parametric version, and it comes in the non-parametric. And it's really the non-parametric that puts the name to this bootstrapping thing. We'll get to the non-parametric. We start with the parametric. By parametric, the name means that we still assume some distribution. It could be the normal distribution. It could also be other distributions. We just have to use a distribution, and then we can do statistics based on that distribution by simulation. Let's try it. So now I want to do statistics on something that I haven't even taught you. Namely, what if I assume that I have some data? Or what if I have some data, you could say, for instance, waiting times in a call center. 32 seconds, 1.6 seconds, 42 seconds. And I've already learned previously that when I have waiting times in such a random system, probably the exponential distribution is the best immediate guess of which probability model is the right one to use for such outcomes. How could I then, but then I still want to do statistics for the mean, just like I taught you before the break. I want to know the mean, and I want to know the confidence interval for this mean. But the data is not normal. And I only have n equal 10. So the CLT, central limit theorem, probably pushing it a bit to try to believe the CLT with just n equal 10. At least I don't know how wrong or how right it would be. So probably the t distribution coming is not maybe the right thing to use here. What should I do? Well, we proceed almost as we have done so far. I compute the mean of the numbers like I've been used to. The mean waiting time is 26 seconds. For the lambda then, it's 1 over 26. So to be able to use an exponential distribution with the mean of 26 seconds, right? So I emphasize, this is the parametric bootstrap thing, that I assume, may be right, it may be wrong, but we use the assumption that this system is described by an exponential distribution. What is the confidence interval? Yeah, this is rephrasing. The only thing I could have answered until 5 minutes from now would be, I don't know. You didn't teach me. Here it is. It's not difficult. The same idea as before. I set the number of simulations. In this case, I chose 100,000. I set the seed that just, if you want to reproduce, it's not important, setting the seed. If I don't do it, it'll do it by itself, as I said. And here it comes now. Let me tell you what's going on here. Here, I simulate, I sort of redo my experiment here. I let the computer do my experiment many times for me and to see what happens in such an experiment, right? It's kind of others could call it a kind of sensitivity analysis on my computations. This is a phrase that people could use in other contexts if they're not in a stats class. So I simulate from an exponential. I have to simulate from the right exponential for it to make sense. So I simulate from the exponential with the right mean, using the data to compute the mean, right? Then I replicate this 100,000 times. So 100,000 times I do my experiment with 10 exponentially waiting times. Can you see that? I simulate the sampling distribution. I don't rely on theory telling me how does the mean of 10 exponential behave. Could I find a probability distribution to do my statistics? Yes, probably some people could. But hey, I don't care. I don't want to take the class. I just do it myself. One line in R, and I've done it. Then I use this apply function, which is just a sort of bookkeeping thing in R that takes all of these 100,000 by 10 or 10 by 100,000. I always forget whether it's one or the other way. I have to jump into R to recheck whether it's rows or columns, which is rows and which is columns. I always forget. I compute the mean on one dimension 100,000 times. So I get 100,000 means, right? Each time that I simulate 10, I compute the mean. And then, I think before looking at the quantiles at the end, let's just make basically here's the sampling distribution. Whoop, magic. You should spend a few classes of probability theory to find out what is the sampling distribution of the mean of 10 exponential variables. I need a lot of theory to know about that. And other people at Copenhagen University will spend some classes also here, because it's nice to know, but I'm giving you the lazy entrance to some of this at least. I just look at it. Hey, this is what can happen. This is what can happen. Then I just read off the confidence interval. That's the principle, right? Here is the sampling distribution. I just find the quantiles, 2.5%. If I want the 95% confidence interval, I extracted from those 10,000 numbers, or 100,000 I think I had here. I just used the definition of a quantile that I gave you in chapter 2 on getting started with everything, the raw empirical quantile. And now I just use I use the default choice of R here. You read chapter 2 if you forgot the details. There are different versions of quantiles. I give you one in chapter 2. There are a number of different ones. It's not important, all of these different definitions. They may give slightly different results, but it's not important. I just take the 2.5% and the 97.5% quantile, read it off. Here's my result. This is the confidence interval from 12.6 up to 44.6. Confidence interval for the exponential mean of 10 in 2 minutes. You would have to take 1 or 2 classes more here. I don't even think we teach it in some of our classes here explicitly, apart from me. You're so lucky. Yes, question? How do I know that I'm supposed to use 95%? Well, I don't. Yeah, just as an arbitrary choice, but the choice mostly used by most people on the whole globe. So it's just a standard choice. So we jump to the next one, Gandalf.